All right, welcome to another working session for the Wolfram Physics Project. Our subject today, as last week, is going to be mostly about experimental validation and verification of our models and trying to connect what we're doing to things that can actually be measured. I have to say that we've been off a little bit in the wilds of more theoretical kinds of things recently. I've been working a lot on metamathematics. Some other people have been working on sort of numerical analogs of multiway systems. I would say that some of the things that there's some really quite exciting things which are, I think, in the offing to do with connections between multiway systems and numerical multiway systems and ideas about complex functions and so on. And I almost feel like we should look at that today. Also, in my metamathematical adventures, that the main thing that I've been trying to do is to both make a theory of metamathematics using ideas from physics, but also use our intuition about mathematics and mathematical theorem proving as a way to understand more about the structure of what can exist in quantum mechanics and in our models of physics. And I have to say that along those lines, another thing that came up, we were looking yesterday in connection with Wolfram language development at chemistry. And one thing I've known for a long time is that the network of possible chemical reactions is also a multi-way system. And the question of doing chemical synthesis is just like theorem proving. It's a question of finding a path through that network of chemical reactions. And I mean, a couple of realizations. One is that it's possible that you can think of the chemical rates as being related to foliations of the multi-way graph of all possible reactions. Another thing that has certainly occurred to me is, when we think about biochemistry and the things that happen in living systems, usually we are used to tracing out particular paths that are taken in chemical space. But the question that I was wondering to myself is, could in fact it be the case that some of the things going on in biological systems are actually using the multi-way system, so to speak, not tracing out particular paths, not doing things like avoiding race conditions by using protecting groups and things in chemistry. Anyway, those were just some things I was thinking about. And Jonathan was just showing me the results that he was getting about Euclid using multi-way systems and so on. I mean, part of the question here is what can be compiled to a multi-way system. We know that a lot of quantum formalism can be compiled to multi-way systems. Mathematical theorem proving can be compiled to multi-way systems. And in a sense, multi-way systems represent sort of a paradigm for thinking about things, which we just need to understand more about. I mean, back in the 1980s, I tried to understand how to make programming environments for parallel computing. Didn't really succeed, thought about using graph theoretic kinds of ideas. Maybe we're at the point where now we've got enough things coming into multi-way systems from all different angles that we have a chance to sort of understand them at an intuitive level and be able to make progress with that. All right, but we were tasked with talking about experimental validations, investigations of our models. So let's get to that. All right, so the first big thing, we've got a number of categories of investigations. One have to do with space-time. Another that we didn't really talk about last time very much is quantum mechanics. And we also didn't talk a lot about, okay, so there's a category of things that I suppose, well, let's maybe start another notebook here. Okay, hold on here. All right, so I would like to redistinguish well, maybe I can do that here. Okay, so there's sort of new indications of things to look for. So there's discreteness of space and time, there's dimension change. And I guess in the subject of dimension change, one of the things I wanted to do was to make a collection of formulas about physics that work in d dimensions. And maybe we can just outline physics in d dimensions. So I guess we need to sort of fill in the different areas of physics. So let's say classical mechanics, electrodynamics, gravitation. Then we have all sorts of quantum effects. Okay, and we also have quantum field theory. Okay, so let's talk about things in d dimensions and what, what are sort of standard, I'm almost feeling like I should just pull up a collection of standard formulas of physics. In fact,
Would you want to include thermal physics on the list, or is that going to be included
thermodynamics
in classical?
I don't think thermodynamics is going to be at all different, but we should include it. And I'm let me see, I'm just trying to remind myself of sort of the gosh. I mean, there's all sorts of things that we can compute. I mean, there's all sorts of things about materials. Okay, so let's say another piece to this whole picture is materials. Okay, so then we've got like crystallography is one area where we certainly have different numbers of Bravais lattices and things, but we certainly don't know. So I think crystallography is going to be hard to do in arbitrary dimensions. In other words, we can do it in integer dimensions, but the question is, what can we do in continuous dimensions? Okay, so like in quantum field theory, the big issue is renormalization seems to be very four-dimensional. I don't know whether it is. I mean, we certainly have dimensional regularization as the method of writing down many formulas, not in specifically 4 dimensions. But I was hoping we could maybe we could do some. I mean, I wanted to really make a collection of all of these different formulas of physics in like, Maxwell's equations. To what extent do Maxwell's equations depend on being in d dimensions? I depend on dimensionality. I don't think the equations, well, like let's say Maxwell's equations, and at some level we've got, the whole, what is it called? Box. What is that thing called? See, this was the thing that I thought was going to happen, and I was concerned about this. Okay, hold on.
Wait, are you trying to get the D'Alembert operator?
Yes, I am.
Slash square.
We've got, I mean, I don't know. And again, maybe this is the wrong, maybe we should be thinking about this offline. I'm trying to fill in, clearly we've got Maxwell's equations. We've got things like inverse square law, which are no longer the inverse square law, right? They're, okay, we got some math, basic math. We've got the,
curl.
What's that?
Generalized curl, which you need for Maxwell's equations.
Indeed. Well, so in basic math, we've got hyperspheres, and we need the formulas for volume or generalized volume. We need surface area, which we should actually fill in the actual formulas, which I don't have offhand. We need, well, so, you know, the inverse square law is going to be basically 1 over area of d-dimensional sphere. Another can of worms that we'll have is units, e.g., you know, what are the dimensions of the gravitational constant and so on. Units, you know, some don't depend on dimension. Others, like G, do, right? Because G is a constant of proportionality between curvature and energy momentum. And I think I worked this out a few months ago in connection with some of the estimates for the physics. But again, I mean, this is something we need to start filling in. So gravitation here, we've got, for example, black holes. We know there is d-dimensional. Okay, you're sending me something in chat. Yeah.
Yeah, that's an easy one. That's just the volume and surface area for spheres and n dimensions.
Right, which we can, well, yeah, let's write it in. Volume claims to be pi to the d over 2 divided by d over 2 factorial. Let's just check that that's right. Oh, times r to the d. Shayamal on our live stream is suggesting that we should be doing this as handwriting input. Yeah, actually, I was thinking about doing this with like tech-like stuff, because it turns out in the new version that we have, you can actually directly enter stuff in, and I may use that here. If we find formulas that are in tech, I can actually just enter them directly, hopefully. But let's get the surface area. Let's just check that this is right. See, this is the big advantage here, is we can just make a table of that. D goes up to 4, and there we go. Nice. Okay. All right. Surface area is, we could obviously get that by differentiating. We can also just get that by looking it up here. So it's, let's see. So the surface area is 2 pi to the power, so let's see, it's d plus, no, the d-dimensional, the surface area of a d-dimensional sphere is it this, or is it, yeah, I'm sure we have that.
I think it's easier just to differentiate with respect to R, the volume formula.
Okay, fine. I'm just curious if that will work. No. Okay. All right, is that the answer? I think that will be the answer. Okay.
So,
Okay. All right, so now the inverse square law is just given by this thing here. All right, so what I mean, again, I feel like we should be putting
I think my personal view is the place where this gets interesting is when we start talking about differential operators, right? Because that's where some more serious math starts to come to play.
Yeah, all right. So I mean, the next case is
because I think Maxwell's equations in higher dimensions are actually mathematically non-trivial, and the reason for that is that the div, grad, and curl operators are the three exterior derivatives of in R3. So you can generalize them by viewing them as being basically, they form the non-trivial differentials in some de Rham complex. And so you can generalize that to an arbitrary dimensional manifold, but it involves some interesting stuff related to the Hodge star and musical isomorphisms and things like that.
Right. Well, so the question is, because one of the things that's a bit mysterious about quantum field theory is it seems to be like quantum electrodynamics seems to love 4 dimensions. And renormalizability just doesn't seem to be a thing outside of 4 dimensions for, let's say, specifically quantum electrodynamics. But my guess is that's a consequence of the fact that, I mean, there clearly are theories in which there's renormalizability in different random numbers of dimensions. And the question is, it's a consequence of presumably the particle content of QED and things like that. I mean, the usual formulation of phi to the n field theory, right, is, it's renormalizable in n dimensions, basically. But I think, if I'm right, anybody know this? I'm pretty sure that's correct, that phi to the n field theory so not certain that's correct, but I think that's correct. So in other words, you're changing the, well, at least you're changing the couplings between fields, to get renormalization. But again, QED, again, I don't know to what extent the fact that QED appears to not be renormalizable outside of 4 dimensions is a consequence of the way that we set up QED, and to what extent it's a consequence. In other words, could we imagine something which is like quantum electrodynamics, but which is renormalizable in 5 dimensions, for example? Maybe that's a known and obvious thing. I don't know. But do you want to say some more? I mean, with respect to differential forms, we obviously have, we have wedge products and things, which are, where AKA curl, etc. Now, we have a generalization, don't we? We have this notion of, what do we call it?
So we have tensor wedge, and we have also Hodge duals, etc. Now, I was thinking about Jonathan's comment. Perhaps curl should be avoided when thinking about other dimensions for electromagnetism. I mean, it's still true that there is a vector potential, which will have now more components. And it's also true that there will be an F mu nu.
Sure.
And then we can take duals, etc.
Right. So F mu nu, the field strength, is then corresponds to that is a
so that will be derivative mu of 8 nu minus this antisymmetric.
Now I'm going to live dangerously and try and use something which is in a sense very old technology, but I wonder whether this is going to work. If I use in our newfangled thing, let's see whether I can do this. Let's try and insert tech. Of course, I don't know how to do this in tech. How do you do this in tech? Is it \partial sub? Is that right? Is that correct, tech?
Yep, that works. You're a natural.
So I haven't done this in years. Let's see. What am I doing? I'm doing d mu. What am I trying to do? I'm doing what is the field strength in
So partial mu A nu minus, and then change the indices.
oh yeah, right. Okay, minus, and then that same thing with the indices switched. Oh, look at that. That was exciting. Isn't that cool? You know, we've had the technology to do this for 25 years. It's unclear why we haven't done this. There's some kind of weird selection bug in this version. This is just the preliminary version. Let's see. I don't know what that actually does if I paste it in here, but let's try and see what it does. Well, it looked good. That's very promising. Okay. All right. Okay. So, yeah, Parmenides is commenting that Kaluza-Klein theory is five-dimensional, absolutely, and has the same form as this, if I'm not mistaken.
Sorry, can I just return to the point I was making earlier? So, the point I was trying to make was that I think there's usefulness in thinking about this as a chain complex over using geometric algebra for the following reason, that someone, maybe Jose, can correct me if I'm wrong. I'm not aware of a natural extension of geometric algebra to non-integer numbers of dimensions. But the notion of...
Yeah, there isn't. That's, yeah, okay. So you're going to claim there is a way to do that with these chain complex things.
Well, I mean, okay, so what is it that defines a chain complex, right? It's just the property that a composition of two consecutive differential operators should be equal to 0. So you can just write down some defining equation, di plus 1 composed di is equal to 0. There's nothing that says that the indices in that defining equation have to be an integer. I mean, obviously, in the conventional intuition, they are. But the chain complex equation, I don't see an immediate reason to assume that that the i's have to be integers.
Walk me through. Okay, so one approach to all this stuff is exterior calculus and differential forms and so on. That's what you're saying we shouldn't be using.
I'm not saying that we shouldn't be using them. I'm just saying I think there's another way of looking at it, which, to my mind, may extend more naturally to non-integer numbers of dimensions.
Oh, well, let's look at it that way. I've never looked at this. So can you walk through how this works?
Sure. So if you think about things in terms of the differentials appearing in a de Rham complex, so div is d naught.
Okay, let's do some basics here. Okay, yeah. Let's start with de Rham cohomology and the whole shtick. How do we build this up? What is the story here?
So what you're doing is you're building up a cochain complex of differential forms, with the based on the exterior derivative.
Okay, but what does that mean? What do you mean by?
We're starting from 0, then we're applying one.
Okay, so we're trying to make one of these sequences, one of these sort of.
Yeah, exactly. So then you'd apply.
We're trying to make an exact sequence, exactly, perhaps.
Right. Yes, it is an exact sequence. So 0 would then go to the space of smooth functions on your manifold.
Okay.
And then you apply a differential operator. Which in this case would be an exterior derivative, and so if your first thing is like omega 0 on your manifold, then the next object would be omega 1, and then the next object would be omega 2. So each time the next object you're getting is obtained by applying an exterior derivative to the previous object.
And why does this end?
So
in d-dimensional in integer dimensions this ends, but
yes,
in non-integer dimensions it doesn't end.
Right, precisely, yes. So this would be a this would be a terminating exact sequence if you have finite numbers of dimensions.
Okay, so let's just, because I always like to see these things explicitly, let's just do this explicitly. So let's walk through an example. So we make a function here, which is a function of, let's say, n variables, right? So I'm going to make a smooth function here. I'm going to make the function, I don't know, let's say, let's make a function which is, some weird, ugly function. So let's make a sum of x sub I to the power x sub j, I goes from up to dimension d, whatever that's going to be, j goes up to dimension d. Okay, very weird thing, but I just want to make sure that no derivatives vanish before their place, so to speak. If that makes sense. What's that?
That's a good idea.
Okay, so let's say with d equals 3, let's say, what does this thing look like? It'll be a big hairy mess. Okay, there it is. Okay, so now we apply this. So this is a scalar function, right? Scalar function of these coordinates. That's one of these things here, correct?
Right. Well, that's an element of that thing. Yeah. I mean,
exactly. So
the
then
zero...
this is the grad. This, for what we want to do here is make the gradient of this, correct?
Right. Okay. So in the general de Rham context, you would think of so you start off with the space of smooth functions, then you would go to the space of one forms, and so on.
Indeed. So that's a one form there.
Right. Exactly.
And that's a two form, and your point is, okay, so then there you go. Okay, so what is the one form that you get from this? So the one form you get from this is essentially a gradient, if I'm not mistaken. This is d with respect to each of those xi, whatever, right?
Yeah, precisely.
Okay, so let's write that down. So that is equal to d, let's see, can we do this? If we say, what's a good way to do this? Let's do an outer, which is really going to reflect the, let's say, scalar there. Okay, so then let's say outer of d of scalar, no, d, oh. Actually, what we're ultimately going to be doing at each level is an outer. Is that correct? Or am I confused? Or do we need, is it instead our tensor wedge thing that we're doing at each level?
I think it's a tensor wedge.
Jose?
I'm not fully sure about the operation you want to do.
Well, I'm trying to compute a one form by taking an exterior derivative of this object here. Right? What's the exterior derivative of the scalar? Answer, it's a gradient, right?
Yes, you could start just with a gradient of yeah, and provide the coordinates.
Well, you're saying I could just say grad of scalar, and then the coordinates are array x d. Is that correct? Okay, big mess, but there it is. Okay, so importantly, it's a three-element vector, right?
Right.
So then what you say is, we're going to go, let's make the two forms here. How do we make the two forms from this? What we need to do is make a tensor wedge. No, what are we doing here? We would normally have an epsilon ijk. We'd have a totally antisymmetric tensor. We have the outer product with a totally antisymmetric tensor, yes?
Right, exactly.
Which is otherwise known as a tensor wedge of something with something. But I'm a little confused here. How do I compute? Jonathan, do you see how to do this? I mean, so we have div grad and curl, but we don't have an exterior D, although we could have one, right?
Yes, right. Which is what you'd need in general.
Right, so we should define an exterior D, and the exterior D of a, in general, of a P form, and then we might have to give coordinates, yes? Is that right? Depending on the rank of the P form. What's that?
It should be possible to do it coordinate free, I think.
Well, not if we have an explicit formula here.
Yeah, sure. Not in this case where you've already kind of put in the coordinatization.
Right, but what is the formula for this exterior D for a P form?
Steven, try a symbolic tensors backtick exterior D, which we were exploring some time ago.
Why did we never implement this? What do I do here?
I don't remember right now, but there were still some design issues. So
time to put it in the function repository.
Now you can put the vector of three coordinates, of three components of three coordinates, and then x, y, z.
Okay, so then this, but that would work if this was a, how do you represent a two form, for example, here?
So these, provided a vector, it's going to return an antisymmetric tensor. Let's see.
Oh, I didn't set D.
It's outside the width. Your array is outside, yeah.
You're missing a comma.
And after the array, the first array XD, yeah.
Okay, exotic. All right,
Right,
so
so
if I were to look
normalize
at the
that.
normal of that, I should see a bunch of zeros on the leading diagonal. Why do I see zeros there?
Well,
So
there are zeros on the leading diagonal.
Right.
But there's
minus
additional
signs.
zeros here as well.
Yeah, so that may be the structure of the.
Oh, it's because I've got symmetry. That's right, because my function is a symmetric function of I and j.
Yeah. So in principle, now you could do exterior D of this guy again, and then you would get a 3, 3, 3, etc. And this terminates because exterior derivatives can only go up to the dimension.
Right, so let's watch that happen, just for fun. Okay, let's just watch it. So what we're going to do here is we're going to take a hash here, and we're going to do, a nest list.
Right. So
What's that?
perhaps you can start with a just a function, general function x.
Oh yeah, maybe that will work. Is that going to work? Function, well, actually I need to put my width outside of the whole thing.
Well, there are two kind of limitations here. One is that exterior D of exterior D is going to be 0. And the other one is that an antisymmetric tensor cannot go beyond its dimension in rank.
Indeed, indeed. But I don't see that happen here, okay? So for this, what do I want to do? I want to apply F to array X comma D, correct?
Right.
Okay, so let's go like this. Oops. Okay, so there we have the F. We have, why does that go 3, 3 there? Why is that not just a 3?
I'm confused now. It seems to be jumping in steps of 2. So perhaps, oh, you have a grad there. Yeah, you have both exterior D and the grad. So you are differentiated to 1.
Yeah, okay, so let me get rid of the grad and just do the exterior derivative there.
Right.
Okay, all right, better. Okay. What the heck is that?
Okay, yes. So here you are being exposed to the full internal language of these things, which is keeping track of covariant, contravariant, etc. Yeah, I forgot about this, sorry.
Do I care? I mean, in other words, this is, okay, so this is a symbolic tensor, but is it the case that if I go and I take that symmetrized array, let's say I go 4 times here, you're going to say that symmetrized array is going to just be 0. If I get out that symmetrized array.
Yeah, I'm expecting it so.
Boom, it's 0. Okay. All right, so what this is saying is, as you take so in the ordinary case, we're taking these exterior derivatives and Jonathan's chain complex is landing at a big fat 0 after these steps. If it wasn't interdimensional, each one of these would be a, I really don't quite understand. I mean, coordinate free, we wouldn't be having actual derivatives here, but we'd having something which at every application of the exterior derivative, we're changing up to a P form, right? but that never terminates because there's never a place. So thought about in terms of hypergraphs and things, what we're talking about here, as we add more derivatives, am I correct in thinking, if I think about this in terms of hypergraph, at every node, okay, we got a function painted on a hypergraph. Okay, so imagine our original function is painted as a scalar, so to speak, on the hypergraph. If that makes sense. So every node of the hypergraph is given a value. Okay, then what does the exterior derivative do to the hypergraph? It must update at what it's doing is at every node, and that's where all this cotangent basis should come in, I think. At every node, so original function is just painted as a scalar at every node. Okay, so then the claim would be after one derivative, we see the finite difference. We see every individual edge painted with the difference between the value at the two ends of the edge. Is that right? I'm trying to do finite differences. Jonathan, Jose, do you understand what I'm talking about?
I think so. I mean, it would be nice to find the equivalent here of the standard formulation of the boundary of a boundary zero, which is what the d squared is doing. So perhaps there is a geometric way of approaching that from the graph point of view.
Right. Jonathan?
I'd quite like to complete the thought I was trying to articulate earlier, if that's...
All right, okay, go ahead.
The point I was trying to make was that we don't need exterior algebra for this, right? So you are constructing the chain complex explicitly in terms of exterior derivatives, but you can also look at it from the other way around. You can define the exterior derivative in terms of the chain complex. So the definition of the chain complex is anything for which the composition of consecutive maps is zero, right? So in the case of, in our case, if we have this thing be a three manifold like you have here, then grad is d0, curl is d1, div is d2, and so then we're just saying curl of grad is 0 and div of curl is 0, and somehow those are the defining identities. And so the point I was making is that you can define their generalizations purely in terms of the defining equation of the chain complex. You don't need the exterior derivatives at all. The fact that they happen to correspond to exterior derivatives is that's where the intuition comes from. But once you have the chain complex, that's a purely symbolic object. And so the point I was trying to make was that in the general hypergraph case where you don't necessarily have integer dimensions, you can still have the equation di plus 1 composed di is equal to 0, even if the i's are not integers. That's still a meaningful thing to say.
Well, I mean, in this sequence, right? Each level of the sequence, you're adding another derivative, correct? I mean, that's what you're saying. Whether you're calling it a chain complex or whether you're talking about it in terms of differential forms, the point is that each successive step, there are integer steps you're taking. Each step is adding a derivative. The question is whether you ever end at 0. Did I miss something?
In the geometrical algebra, if you're constructing the chain complex directly using geometric algebra, using exterior derivatives, yes. I
don't understand the other case. Explain the other case. I'm confused.
No, the point I'm trying to make is that the defining equation of a chain, okay, with an ordinary chain complex, because you are doing something like you're applying boundary operators or differentials or whatever, you would think of it as being a discrete integer, integer number of applications thing. The point I'm making is that the defining equation of a chain complex, di composed di plus 1 or di plus 1 composed di is equal to 0, is somehow more general than that.
Okay, what is di?
The ith differential operator.
So the operator here. So what are you saying? So this chain, okay, so you're saying in this idea of a general chain complex, okay, you're saying, so explain what you're saying. So you're saying the operator,
Okay, so you have a chain complex, you have some algebraic structures, groups, modules, whatever they are, and then they're connected by some homomorphisms. And the homomorphisms are interpreted as these differentials, right? That's the basic idea.
I understand. So you can think of that as an operator acting on the thing, you know, the first thing acted on by an operator gives you the second thing. Is that right?
Right. So in other words, what you have is a family of homomorphisms, a family of differentials,
Yes.
if you want to call it that satisfy the equation, you know, di composed di plus 1 is equal to naught for all I.
Okay, right. So what you're saying is...
What I'm saying is that that although they're conventionally indexed by integers, there's no reason that the chain complex equation di composed di plus 1 is equal to 0 works even if the homomorphisms are like an uncountably infinite family parameterized by real numbers. There's no reason, you know, there's still a meaningful notion of a chain complex. Even
I agree. Right, the homomorphisms going to successive stages in the chain complex satisfy.
So the reason why I think this is nice is because we know that in the integer dimensional case, it preserves all of the properties of exterior derivatives and so on, but it generalizes to, you know, non-integer numbers of dimensions.
I get it, but this is basically the same thing as Jose was just asking about the boundary of a boundary being 0, isn't it?
Yes, yeah, that's exactly that's the condition.
Right, so I mean, what this is saying is these i's, but the i's don't have to be the integers, right? Which is kind of the same thing we were saying up here. That, you know, we could just start with a hypergraph, you know, and this di plus 1 operator, whatever it's doing. So I was just trying to describe what those operators would do, right? So I'm claiming that what is the general definition of one of those operators? So I'm claiming that the general definition is you somehow take this, look, you know, here, the 0th thing that we've got here, I want to try and construct explicitly what this is, and I think we're quite close to being able to do that. Because I think what's happening is that you have some set, and you're either dealing with the set of values painted on every node, or you're dealing with the set of values that are painted on the edges, forming the difference between two nodes, I claim. Maybe this is the wrong way around to think about it. Maybe we should think about it in terms of hyperedges. Do you see what I'm, and then the next order thing I claim is going to be doing the same kind of operation of taking these differences. That you're going to get more differences, okay? But if you do this for like a regular 3-dimensional grid or something, it's going to limit out in the same way that this does, because you don't get to take differences of differences enough times. Does this make any sense? Oh, Jonathan, you get what I'm talking about?
I maybe. I mean, can I try and reformulate what?
Yes.
Is going on? So, in the case of a one form, okay. So suppose you have a hypergraph. It has an ordinary number, an integer number of dimensions. So we can import all of the standard methods from geometric algebra. So you could pick a particular geodesic, and you can then do finite differences along that geodesic, and that will give you the analog of a one form, essentially. Right.
Right. Or what I was doing was I was just saying, consider every pair of nodes and compute, which is like a little tiny geodesic, right? And attach to every pair of nodes this number, and that's the analog of a one form.
Except that at the level of a single hyperedge, you can't really construct meaningful notions of orthonormality. Well, you can, but basically what you're saying is that every pair of hyperedges that aren't parallel are orthonormal.
Yeah, right.
I would argue what you need is something, you want something with finite extent. You want a geodesic, and then we have a notion of orthogonality of geodesics, right? You can just ask, if you have a pair of geodesics emanating from the same point, you can define them as being orthogonal if the shortest distance between all points on the second geodesic to the first geodesic are, if those shortest paths all go to the origin point, then you can define them as being orthogonal. And so then, if you're computing derivatives across a pair of orthogonal geodesics, you're essentially taking a 2 form, and so on. And then the reason why this generalizes naturally is because you could have, in hypergraphs that have non-integer numbers of limiting dimensions, you can have pairs of GD6 that are kind of neither, behave as though they're orthogonal, but they're not, they're not actually orthogonal, so to speak.
Well, wait a minute. So first claim is that, and again, we're getting off topic here, but the other Jose R, pasted something in here about a quote from John Wheeler. The boundary of boundaries zero, central principle of algebraic topology, is the unifying theme of Maxwell's equations, Einstein geometric dynamics, and almost every other version of modern field theory. Yeah, well, okay. Inspires hope that we will someday complete the mathematization of physics and derive everything from nothing, all law from no law, said John Wheeler at some point. All right, so he thinks the boundary of a boundary statement is incredibly important. So maybe we should understand the boundary of a boundary statement more carefully. All right, so this is now, we're careening off topic here, but anyway, let's go with this for a minute. So we're talking about construction of p-forms. And we're saying that, I mean, you're making the claim that we have to have somewhat long GD6 to have a clear notion of
right, but I think everything else about your intuition is basically right. That the one form case is where you have a GD6 that's just oriented in the direction of a particular hyperedge. The 2 form case is where you have a pair of GD6 that are oriented in the direction of 2 hyperedges, and so on.
Right, but so let's understand the boundary of a boundary statement, okay? So what we're saying is, we've got to make a p-form. What we're doing is, roughly, we're taking, okay, to make a p+1 form, this is where we need to understand the generalization. P+1 form from a p form, we are basically taking finite differences, okay? And we're taking finite differences somehow in all possible ways, relative to the numbers effectively in the p form. Okay, what do we mean by that? So in all possible ways, following the hypergraph. Okay, so what do we mean? What we mean is, given a set of numbers, right? So we've got some graph. So let's say we have a grid graph of a 6 by 6 grid graph, okay? So we're going to put a number at every one of these nodes. And then what we're going to do is we're going to compute the first level. We're going to compute differences and we're going to label edges. Okay, well, we can label runs of edges, but let's for now just label an edge. Okay, so then that's so we can we do this explicitly? Can we just do this? Can we put like random integers on the weights here? How do we do that? Anybody know how to do that? How do we add vertex weights here? We just say graph vertex weights arrow, and then let's say table I goes to random integer. Oh, let's say random real, just to be more random real. I goes up to 36. Is that right? And then if I want to, I can just say vertex labels arrow vertex weight. Am I right? Well, that's rather silly because they're, okay, there we go. Okay, so there are our weighted values, right? Okay, so the first finite difference would label every edge here by the difference between those two values. Make sense, guys? Hello?
Yeah.
Okay. Okay. So, Jonathan, do you agree?
Yes. Yeah.
Okay, so that's the first level, right? We're taking differences in all possible ways here between neighboring points, right? Okay, so now we've got edges labeled, right? Next level, we've got edges labeled. Now what do we do? Now what we want to do,
you want pairs of labeled and so on, right?
Say again?
Then you want the pairs of edges to be labeled for the two-form case and so on.
Yes, but how do we actually do that? So what we actually do is, and this is going to work nicely. The boundary of a boundary thing is going to come out nicely here, guys, I think. Okay, so the next level.
I really don't think you need to use geometric algebra to get that result. I just don't.
Which result?
To get the boundary of the boundary thing. I just don't think it's necessary.
No, but we're trying to understand the intuition of it with hypergraphs.
I know, and I don't think it's necessary to use explicit derivatives. I think you can do it just with the structure of the cochain complex.
Okay, well, just humor me for a minute so I can understand this, and then we can go back to the cochain complex, which I don't understand how that relates into this.
Well, again, do you mind if I just say for one moment, I mean, how that would work?
Okay.
So if you have, okay, so the notion of a boundary in an arbitrary graph is very easy to define, right? You can basically define it by a centrality measure. You say, let's take a subgraph, and then you can just ask, if we look at all the vertices in that subgraph, and you look at all the geodesics that emanate to all other points in the graph, along all of those paths, there will be a final vertex in the within the subgraph that will be traversed in each of those paths, and the set of all such vertices will form the boundary. Right.
Okay, so what we're doing, we're saying, let's just do it just for a second, okay? Just so we're keeping things sort of straightforward. Let's pick a random graph. Let me just pick something up here. Hold on one second. I just want to be explicit. Let's see here. Let's pick one of these. Let's say, do we have a states graph now, or final state graph? Is there a final state graph thing anymore now? No. Anybody know whether there's a final state graph?
Are you thinking of final state plot?
No, I'm not thinking of that. I'm thinking of a graph. I want a graph object. Okay, no matter. We'll just get it here. Okay, there's a graph. GGG is our graph. Okay, so now what you're saying is, let's make a region within that graph. So let's say highlight graph of GGG of neighborhood graph of GGG, comma, let's say node 5, comma 2 steps. Okay, all right, there we've got our subgraph, right, Jonathan?
Yep.
Okay, so now we consider geodesics that originate within the subgraph and go to other places in the graph.
Exactly.
And there is some place in which they poke the boundary of this subgraph.
Right, so basically what you're doing is you're generalizing the notion of like betweenness centrality or something, but instead of generalizing it to a particular vertex, you're generalizing it to a collection of vertices, and you're just asking all the shortest paths from a point inside the region to outside the region will go through as the final traversal through that region will go through a vertex in a certain
vertex, and you can essentially paint the surface of that subgraph by how many such things going to all possible other points in the graph, how many such things went through each of those, and that will give you, that is some kind of betweenness centrality measure.
Right, and so in particular, that subset gives you the boundary. So then you can ask, well, what's the boundary?
Wait. I see the boundary. Okay, so let's just do that here. Let's just do that, just for the sake of definiteness, okay? So we're going to go from every edge.
Every vertex, no, you have to go from every vertex inside the region to a vertex outside the region.
Right,
and then
right. So let's say all possible ways to get from that vertex, right? So this is, now is it, okay, so we want the complement, right? So let's say vertex list of this. So this is the inside, is that, right? If I'm not mistaken. The outside is complement of vertex list of GGG, comma, inside, correct?
There's a parenthesis, yeah, around GGG, but that's, okay. Yeah, I think that's okay. And then, so then you're just asking if we pick a point on the inside and we pick a point on the outside, and we make a geodesic from one to the other, then there is, in each of those paths, there will be a final vertex that you traverse in the process of going from the inside to the outside.
Okay, so then we take an outer of, we're going to get outer of the shortest path from one to the other, okay?
Right.
Find shortest path,
which might be
in GGG of the first thing and the second thing, going from inside to outside. Okay, so that's going to be a big mess of stuff. Oh, interesting.
It's a digraph.
Okay. It's a directed graph, right? Okay, so a lot of things can't go from there to here. Right, so okay, so that's the shortest paths, and so we then complement out everything that's in the inside here, right? Actually, let's complement the outside and look at the last of things complemented with the outside.
Precisely, yes.
Okay, so let's say complement of that. Let's see, complement of outside with this, right? Didn't make a lot of sense. What the hell? Oh, did I get the complement the wrong way around?
It may be, yeah.
Okay, so wait a minute. I want to find the things in the shortest path that are not, oh no, what I want to do is the intersection of this, except that what I want to do is I want to delete everything that is not in the inside, because I want to get this. Okay, so here, I want to get the last thing that's on the inside.
Yeah, so intersection with inside and then last of that should work, right?
No, because the order will be lost.
With intersection?
Yeah, intersection will get rid of the order. It treats them as sets.
Okay.
So what we want to do is to delete cases, right, of the shortest path.
Can you do a select?
Yes,
select by
that's a good
select
idea.
member.
Yeah. Select this, and now what we want to say is, oh, well, okay, let's see. Yeah, I can get another function in there. Okay, so then what I want to say is member queue inside, comma, hash, ampersand. Close with select, close that. Okay, there we go. So each one of these, and I guess we can just delete, should we make an undirected graph just to be, or do we think a directed graph is more useful?
I think an undirected would be more helpful, but it might be slower.
Well, let's just do this case then. Okay, so then let's say the last thing for that. Oh, whoops, I need to say last or nothing in the case where, okay. Okay, and then we want to flatten that. Okay, so now, actually, we should delete cases. I mean, we should do a union of these, but then this, if we say highlight graph of GGG, comma, percent, ta-da.
Right, it gives part of a boundary.
Why is it part? Why is it the part? It's the boundary.
Because it's a digraph.
What's that?
Because it's a digraph. It's not. It won't contain everything. There are some paths it can't find.
Well, okay. Let's just do the case with an ordinary graph. Okay, let's just redo this, keeping this. Let's do an undirected edge here. Let's actually do this as a union of that. Okay, let's just do a graph 3D to help visualize this. And actually what we could do, okay, so there we go. So there is our boundary. Should we do a slightly bigger one? But that gives us some intuition about what's happening. So there's the boundary. Do you want to do a bigger one? Let's do the next one up.
The point I'm making is that there's just a very straightforward centrality theoretic version of a boundary that you can define. But the important point is that once you've defined that boundary, you've already truncated all of your geodesics at that point. And so if you attempt to find another boundary, if you attempt to find you look at a different class of, a class of geodesics going from that new set that is the boundary set, all the geodesics have already been truncated. So your boundary ends up being the empty set.
Hold on. I just want to see it just for the sake of, oh, actually, you know what? I'm going to do something slightly different here. I'm going to do this 3 steps here to make a bigger region. It is always so nice that you can do these things so explicitly and actually see what the hell's going on. Okay, there's our boundary. All right. Okay, now what were you arguing?
So now we've truncated all of the geodesics that were emanating from the interior at that boundary point.
By the way, I'm sorry, could I ask you something? In this boundary set, if I make a subgraph, hold on, if I do this, if I say highlight graph.
In my graph case, it should form a loop.
Well, if I say highlight graph of subgraph, I'm not, and this is the non-digraph case of.
Yeah, sorry, in the non-digraph case, I mean, yes, it should form a loop.
Okay, hold on. Subgraph of GGG, comma, let's say percent 311. And then let's say graph 3D. No, it forms some kind of spider. Wait a minute, what the heck is going on here? Oh, because these are disjoint, right?
Oh, interesting.
So this boundary, okay, but anyway, so this is a little bit weird. The subgraph is a little weird.
Right. It's a disconnected.
What we could do, just to indicate something better, let's do the following thing here. Let's do the following thing, just to understand what's happening here better. Okay, so. Okay, so there we go. So the green is the interior and the red is the boundary.
Right. So all we're doing is we're basically applying the Jordan curve theorem in reverse. We know
what? The thing has a boundary.
Yeah, we will. The Jordan curve theorem says that anytime you have a non-self-intersecting continuous loop in some surface, it divides the surface into an interior and an exterior. And what we're doing is we're saying we know the interior, we know the exterior, and we can use that to extrapolate what the boundary curve is.
All right, okay. So generalized Jordan curve to prove that there must be a boundary, prove that there is a boundary, although it's not a connected graph.
Right. So it's not really, I mean, the Jordan curve theorem doesn't consider the case where you have a discontinuous boundary curve, but anyway, we'll ignore that.
Okay, all right, let's ignore that for now.
It's
Okay,
purely
keep
graph
going.
centrality based measure of a way of computing the boundary. So the point I'm making is that now we've truncated all of the geodesics that were emanating from the interior to the exterior at that boundary point, right? So now if we look at the geodesics emanating from the boundary set to the exterior, or indeed to the interior, they're all going to be truncated at the first step, right?
I'm sorry, from the boundary set. So I see. So you're trying to argue what is the boundary of a boundary?
Right. I'm trying to show that it's trivially nothing. It has to be trivially empty because you've already all the geodesics that were emanating from the interior set to the exterior set have now been truncated at the boundary set anyway, and so there aren't any elements of the boundary of the boundary set. They've all been thrown away.
Well, you're saying the boundary. The argument here is the boundary is essentially a point, and if you ask what's the boundary of the boundary, there isn't one.
Well, it's
essentially
not
what you're saying. What's that?
It's a three-dimensional object. It just happens to be one dimension below the object you started from.
No, but let's just do the same construction again to get the boundary of the boundary. Right?
Yeah, that's what I'm saying. Right. If you do the same construction again, all of the geodesics have been terminated at the point of the boundary set. So what you get is the empty set.
Okay, hold on. Let's just walk through this carefully. Okay, so to get the boundary of the boundary, you say the boundary initially.
You can just do the same construction again. You start from the boundary set, and now you have both the old interior set and the old exterior set, or the interior set minus the boundary set and the old exterior set.
Yes.
And then you do the same outer product construction. And so then what you're going to find is that all of the geodesics that go from that boundary set to either the old interior set or the exterior set, they start at a point in the boundary and then immediately move outside. So the only points that so the last point that they go through in the boundary set is also the first point that they go through in the boundary set.
But you're saying the boundary is a thin thing. So if you say what's the boundary of the boundary, what are you saying? I mean, you're just saying that the boundary. Try this again. You're saying we do the boundary. The construction is done again with respect to. Okay, first we were asking what's the boundary of this green region, right? And we got the boundary of the green region, right? Now we're asking what's the boundary of the red region. Am I correct?
Yes.
Okay, so to get the boundary, our construction method is we start from these points. They are our interior. And
right.
We can go in either direction. We can go into the green region or the exterior region. Either one, right? To get the boundary of this boundary, we don't know where anything, we don't know where's outside and where's inside anymore. All we have is boundary. We're presented with the boundary.
Of course we know what's outside and what's inside. The outside is everything that isn't in the boundary set, just as it was before.
How do we know that the things that are inside the boundary set are inside?
What?
Look, we're just shown this boundary, and we're asked, what's the boundary of the boundary?
Right, so we do exactly the same construction as before. We take the boundary set, and we just take the graph complement.
Okay, let's do it. Let's do it, okay? So we've got the boundary set. Let's label my thing here.
Right, and what you will discover is that if you do the same construction again, the first and last elements of all the geodesics will be elements of the boundary set. So the boundary of the boundary is either the boundary itself or zero, depending on how you choose to construct it.
Okay, so hold on, let's just do it. So what we're saying is this boundary here, this is the second boundary, okay? So this is boundary of boundary, boundary 2.
And then, yes, you're right. All we're doing is we're reproducing the trivial measure theoretic argument that says that the boundary of a manifold has Lebesgue measure 0, when immersed in the rest of the manifold.
Okay, so hold on. How do I do this? So I'm saying select shortest path there. What am I doing here? Member queue
boundary.
There, member queue of boundary for this,
Yep.
right?
And then boundary.
And then what do I do here?
And then you need an outside 2 that is the complement of vertex set GGG, comma boundary.
Okay. Okay,
And then
so
you want
that's
boundary.
outside 2, and then I
Boundary
change
clause.
that to boundary there. Okay, and let's look at that compared to boundary. Ta-da!
Right. The same. So as I say, it's either the boundary itself or it's the empty set, depending on how you choose to define it.
Okay, okay. So
And
now
the reason-
I consider this to be a proof, as
Right.
in,
But the actual proof, the reason why that's happened is because you've truncate by doing the first boundary step, you've terminated all the geodesics at the boundary set. And so now all the geodesics from those are either ones that go to the old exterior or the old interior. And all of those have been truncated at that point.
yeah.
Right.
Okay, fine. All right, so now what's your point here? So now,
So I'm saying that this is essentially a purely graph theoretic or a purely measure theoretic way of illustrating that principle that doesn't require you to define explicit derivative operators.
that's all well and good, but if we want Maxwell's equations, okay, our goal is to get Maxwell's equations, right?
Right, and my point is that I think there's a way to do that just involves looking at the essentially the algebraic structure of the differentials without having to give them explicit, without having to define exterior derivatives and things.
Well, but what is a differential here? See, I claim that a P form, which is going to be referenced in Maxwell's equations because it involves 1 forms and 2 forms and so on. A P form you can get by just looking at these differences of values on particular sets of edges.
No, I think we all understand that, and that's the explicit translation of the exterior, the exterior calculus stuff, and that's fine. I agree that will work.
But what you're saying is the non-existence of magnetic monopoles, which is basically the fact that the divergence of of the magnetic field is 0. The non-existence of magnetic monopoles, you claim, is connected to. You claim that you can essentially, given the way you construct the vector potential, you're going to claim that it is inevitable that there are no magnetic monopoles by construction.
Well, but by algebraic properties of the operators.
Yes.
Right.
But let's just see that. So A mu, in this case, is the A mu is given by the it is just on every edge in this hypergraph. We paint a value. We just say there's a value at every edge. And that's the A mu, is it not? At that position, A mu of x, at that position in the space, A mu, which is the position in space is defined by a particular node, and the mu index, we haven't really defined, but it's just saying, look at all of the edges that go through that node. Looking at the value on those edges is a mu, where mu is defined by which edge is it at a particular node, if I'm not mistaken.
Sure.
Right? Okay, so now what are the Maxwell equations? So what is box A mu equals 0? Or in terms of your de Rham chain complex thingy, how do you understand that?
How would I understand the kind of generalized Gauss's law, you mean?
Yes, that's what I'm asking.
Right, okay, so the point I'm making is that this construction we've done here is illustrating the chain complex equation for a special case, right?
It's saying the boundary of a boundary is 0, right? This is the making of a chain complex you can think of as being a boundarification. Every step, you're boundaryizing something.
Right. So the composition of any two consecutive homomorphisms in your chain complex
Right.
is 0.
So this was an example of boundary of a boundary equals 0. Now, there's a higher order version of this, I claim, which is to look not, I mean, this is asking, okay, well, now I'm a little confused. Okay, as we go down this chain complex, what do you think you're constructing on this hypergraph? So we got successive steps in the chain complex. What are we constructing? I think we're constructing the thing that I keep on claiming we're constructing. And that there's a higher order version of this picture, which instead of looking at individual edges, is looking at pairs of edges and so on.
Yeah, no, sure. I'm agreeing. There's nothing I'm disagreeing with there. I'm just saying this is. I thought we kind of established that that's how it worked, right?
But we should be able to do this computation not on individual edges, but we should be able to do boundary of a boundary for pairs of edges.
Yeah, on pairs of edges. Yeah, sure. Right. I mean, of course, this extends to arbitrary p-forms.
Okay, but hold on a second. It's not totally obvious, at least to me. Okay, so hold on here. So,
won't that procedure terminate at some point? That is to say, you consider sort of pairs of edges and then triples of edges and so on until you exhaust the size of your graph.
We are
maybe misunderstanding.
Vertex degree.
Yeah, it depends on the vertex degree, right? If you do that for an individual vertex, if the vertex degree is bounded, then yes, it will terminate. Okay. But if in the more general case, you don't want to look at an individual vertex, you want to look at a clump of vertices, because you for the reasons Jonathan was explaining at the beginning about orthogonality, it's not good enough to just look at individual edge-to-edge things.
Okay.
But yes, you are understanding what's going on. Yes. Now, what exactly is it, Jonathan? What exactly are we doing in the higher order case, in the pairs, in the two-form case? We're looking for every this by looking at what is reached from each node from pairs of edges, not just single edges, I think. Do you think that's right? Jonathan?
Sure.
So in this construction here, it's a little bit harder to draw this, but what we would do is for every one of these, instead of looking at, whatever it was, find shortest path, we need a generalized find shortest path. What the heck do we actually do? How does this actually work? Well, I can see that something like this is going to work.
Well, like I said, I mean, I think the right way to think about it is not in terms of individual hyperedges, but in terms of geodesics. So then, rather than thinking about a single, in this construction, you're thinking about the intersection of a single geodesic with a particular subset, and that's how you're finding the boundary set, right?
Yep.
But then you could look at what are the intersections of all pairs of geodesics with a particular subset, or in particular, all pairs of orthogonal geodesics with a particular subset.
What do you mean particular subset? You mean?
Okay, in this case, we're dealing with basically like the kind of, I guess, the sort of scalar case where we start from a point on the interior set, we construct a geodesic to a point on the exterior set, and we look at what's the last point in the interior set you passed through along that geodesic. You could also look at a pair of orthogonal geodesics, G1 and G2 from that to exterior points, and then you can ask what's the last point you passed along on G1 and the last point you passed along on G2, and then you'll get an ordered pair, and you'll get a higher order boundary set that rather than containing single points contains ordered pairs of points.
Exactly. Right. Okay. So hold on a second. So instead of asking about,
I think that's a reasonably straightforward generalization.
It is. Yes, I think that's correct too. And it's going to give you a surface that is not a two-dimensional surface or whatever. It's going to give you a more complicated surface, right? Because
right. But crucially, the same arguments about boundary and boundary.
Let's just make a note of what we're talking about here. Okay, instead of asking about a single geodesic coming from the outside into the selected region, into the inside region, ask about PGD6 doing this, okay? And then record all p-tuples of points where these GD6 first intersect the inside region. Correct?
Yep, I think that's right.
Okay. Okay, fine. So that gives us...
Well, it depends what you mean by first. It's like, what's the last point of intersection with the inside region?
I was going from the outside.
Oh, sorry. Yes, yeah, so you were. Okay, yeah. That's good. Nice.
When coming from the outside.
No, sorry. You did say that. I just can't read.
Okay.
Coming from the outside into the inside region.
Okay. All right. Okay. So now, drum roll, you are going to claim something about Gauss's law from this. What is Gauss's law in these terms? So the flux, right, is what's the divergence? What's the I mean, I think Gauss's law is going to be fairly obvious from all of this.
Right. So I think an important thing to tackle before that is to understand exactly how the Helmholtz decomposition theorem extends, which I think, by the way, is actually related to the whole relativistic angular momentum discussion that we had. Mm-hmm. Because the key in that discussion was realizing that when you think about fluxes of causal edges, you can decompose them into into net flux in a particular direction and some kind of, and whatever's left over, which is like the curl, effectively, of your edges. And so I think basically the same thing is happening here. The Helmholtz decomposition theorem is saying you can do the same construction with an arbitrary digraph. And then Gauss's law, I guess, is just saying, it is just applying that Helmholtz decomposition theorem to the, to whatever the magnetic vector potential is. Let's
go through this. Okay. First of all, I don't know what the Helmholtz decomposition theorem is actually. What is that?
Oh, so if you have if you have any vector field that's twice differentiable, then you can convert it. You can decompose it into a divergence-free piece and a curl-free piece.
Okay, that fact I knew. I had never heard it called the Helmholtz decomposition theorem. I wonder if Helmholtz knew that was the theorem.
I think it's also called like the fundamental theorem of linear of vector calculus and other kinds of things, right?
Wow. Okay. Well, anyway, I knew that fact. Right. Okay. So decomposition. So let's talk about this. Decomposition. Okay. Jonathan claims this is called the Helmholtz decomposition theorem. That may or may not have been known to Helmholtz. Okay. Decomposition. We can decompose any vector field. I don't know whether it generalizes into a divergence-free and a curl-free part, right? That right, Jonathan?
Yes, yeah, right. And sorry, I should say it does generalize to arbitrary. I mean, it's a little bit harder to define, but basically, when you start thinking about them in terms of these, these cochain complexes and things. So for an n manifold, you have n differential operators that are such that any consecutive pair composed to give the zero operator, and then you're just saying that the last n-1, you can always decompose your field into the last n-1 differential operators.
No, I'm not understanding. So divergence free. Okay, so what you're saying is we can decide in our sequence here. We can put, well, first of all, decomposing a vector field. We're talking here about.
Look, so here's the point I'm making, right? So if we have something in R3, we have something going on in R3, and we have curl and div are giving us D1 and D2 in our chain complex going from D0 to D2.
Yes.
And so the Helmholtz decomposition theorem is saying that you can define that vector field purely in terms of the bits for which D1 is equal to 0 and the bits for which D2 is equal to 0. And the point is, now if you have a chain complex that's going from D0 to Dn, there's a generalization that goes from D1 to Dn.
Okay. Okay, but the objective here.
The idea of the Hodge decomposition.
What's that?
It's implied by the idea of a Hodge decomposition. The Hodge decomposition is kind of the generalized version of the Helmholtz decomposition.
Oh yeah, I've heard of the Hodge decomposition, so I'm at least ahead in that story. And I think we had figured out months ago what the Hodge star operation was in terms of, because I mean we had thought about this whole p-form question before, and this whole point about the antisymmetry of p-forms is associated with the fact you don't know which edge. If you've got p edges, you don't really have a way to label which edge is which. Do you see what I'm saying? And that's why it's natural to have this antisymmetric idea.
Right. It's getting rid of the redundancy of labeling.
Yes, right. I mean, so actually I'm making a p-form from a collection of p edges without knowing which edge is which naturally leads to an antisymmetric object. By the way, not unrelated to the antisymmetry ideas for fermions that we're talking about. This idea that when the edges, if you have multiple edges and they are distinct.
Right. That's some kind of Pauli exclusion idea.
I think so, but I mean it's leading to antisymmetry in, I mean the idea of an antisymmetric wave function. Just walk through this for 1 second. I mean, so the current thinking is, fermions correspond to sort of dangling pieces of a multiway graph. Dangling pieces of a multiway graph lead to antisymmetry. Ones that merge are
well, the point is that the same labeling, if you have a non-convergent branch pair, the same labeling problem applies, right? That you still have, if you could go down one branch or the other, that's the same as saying you could have picked one geodesic or the other. And so you have to have some duality that allows you to kind of transform from one to the other.
Right. But you see, again, this is probably related. I mean, I hate to come back to our coordinatization of branchial space, but this is again related to that. Because, this antisymmetric story, right? You've got a bunch of dangling edges for your multiway graph. So now what you want to do, okay, question. Assuming they're dangling edges, to what extent can you perhaps use Grassmann variables and things like that to label those dangling edges? So the idea is, normally, I mean, when you coordinatize, you're trying to coordinatize you're trying to label places in branchial space based on coordinates. You're trying to map this branching thing into a bunch of values, right? So I'm wondering if you make, look, if your branching thing is a slice through a grid, right? Yeah, this isn't completely stupid, okay? So if your branching thing, let's say you have a grid graph of a 3D grid graph, I don't know, 555 or something here, and okay, let's say this is your, your multi-way system. This is, and it's full of causal invariance, remergings, right? And you make a slice through here. Okay, you can label every point in here. Somehow you can easily label every point. This is mapping to, R3 in this case, because this has the structure, the right structure to be Euclidean space in some sense, right? Imagine now the tree case where nothing merged. What is the natural coordinatization of that kind of object? You're probably going to say some kind of Hilbert space, but I'm asking if you think about it in terms of you have some, think about it in terms of sort of axioms of, I don't know, translation and so on between these different things. There's a...
In the theory of the eternal symmetry, the coordinatization of the tree is given by the p-adic numbers.
By which numbers?
P-adic numbers. These are the numbers in base P, but we can have infinite number of infinite size.
Okay, so your claim, I have to say p-adic numbers are something I always understand only briefly. But okay, so your claim is that in the case of a tree, that whereas here we're labeling, okay, so in this case, in the case of a grid, we label the coordinate points.
It should be said that the causal networks for a multi-way function system are naturally p-adic.
Okay. Let's understand that claim.
The multi-way function system causal networks, the causal relationships are produced by prime factorization. What?
You mean in your completely crazy way of doing causality with primes?
Right. Which is nice for a whole bunch of reasons, but one of the reasons it's nice is because the distance metric is naturally p-adic in the causal.
Okay, I want to understand this. This is very interesting. Okay, hold on, yes. hold on. We have we are incapable of staying to experimental physics. You know that, guys? We have dived into some piece of by the time we're in a de Rham complex, we're not doing experimental physics. Okay, we can label the coordinates by real numbers. And the claim is, in the case of a tree, we can naturally use p-adic numbers. By the way, Jose R, if we can characterize that.
Yes,
if you can make your audio easier to understand, it'd be great.
Yes, p-adic numbers can be interpreted as a Cantor set. Just think about a Cantor set that could be
right, which is dying like a tree.
Yes, a subset of the real line. I would like to share the screen in order to show the tree used in the cosmology.
Okay, go on.
Okay, it's here. This is a paper of Susky and other authors. We have the tree. This is in the case of P equal 2. This is a cellular model of the arrow of time.
Okay.
Where each color is a vacuum, and the tree is the way in which the universe is in eternal inflation. So each infinite p-adic number represents a boundary in the future. It's a future boundary. And
let's understand. Okay. Yeah, I get it. I mean, once you have a tree, you absolutely have eternal inflation. It's like big rips all over the universe type thing. Here, let me share again for a second, and then let me try and oh, that's interesting. Okay, hold on, let me share here.
It is
I want to
like
understand your comments about spinors as well, but let's just do the p-adic numbers for a minute.
It is just to characterize the tree in binary code. If I go to the left, 0. If I go to the right, 1.
Sure, absolutely.
Doing that, I have an infinite large number. And this infinite large number is a p-adic number for p equal to. And this is the future, the boundary in the future in the theory of eternal inflation.
Yeah, I understand. But I mean, if we say, okay, so let's just say,
there is something experimental about it because I am working with Chris in a model of the mathematical proof in order to see the asymptotic behavior of the network of theorem using the model of the tree.
Okay, but so if we just take, let me just remind myself how this works. So let's say we say something like this. Okay, we have a binary tree. Now that is equivalent to, Jonathan, do you have, is multiway function system in the function repository?
Yeah, it's been there for ages, but no one uses it.
Well, I'm going to use it again. As soon as I get back to my numerical multiway system thing, I will absolutely be using it again. Okay, so then here, you say...
We're not using it, to my dismay.
Okay, well, I will be a user, so don't worry about it. Okay, so then let's say hash plus 1 here, and we start off with the number 3, for example, and we go 4 steps, right? And then we make a states graph. All right, so that's our graph from, that's something where things interact, right? If I say A times hash and B times hash, then I will have a pure non-interacting tree. Oh, no, I don't, because those are, oh my gosh, I'm using, that uses the associativity of arithmetic, right?
Right.
Well, okay, so here's how I do it. If I say f of hash and g of hash, then I will get something which is, yeah, then I'll get a pure tree, right? Because there's no merging there, right? Okay, so now, what was your statement about p-adic numbers?
The p-adic number are the boundary in the future of the tree.
Yeah, no, I understand. I understand. What's in the future here? Every node in this tree is labeled by a sequence of binary digits, but we do not have the standard identification for the reals that 0.99999 is equal to 1.0000 because those 2 points are distinct. Those 2 points are not; they don't merge. So yes.
We can be in the real line if we take the Cantor set.
Indeed, but the Cantor set isn't the, yeah, it's exactly equivalent. I mean, this is the same story as I've struggled with cellular automata forever and ever and ever. You know, an interesting question is, what's the correspondence between cellular automata and iterated maps on the interval? Iterated maps on the interval use real topology, and you know, cellular automata use the Cantor set topology. But what was the point that Jonathan was making about p-adic numbers?
Well, okay. So if you remember the number theoretic multiway thing we did the other day, I don't know if you still have that notebook.
I'm sure I do.
We were discovering that these multiway function systems. Okay, first thing to say is that because the causal network, which you say is kind of crazy, and I kind of agree, because that's based on prime factorization, that was directly related, it was kind of trivially related to the depths of these factorization multiway systems that we were looking at, right?
Okay, so here it is. Here's what we were looking at. These are the divisor systems, which I think Jose and maybe Chris were looking at. So these are the divisor systems. These are, this is, did we ever send this out? I forgot to send this.
No, I think
yes, we have it.
Oh, okay, fine. I didn't forget to send it. Okay, good. But so what was your point, Jonathan?
So my point is just that, trivially, the depth of one of these multi-way function systems is determined by the highest exponent of a prime power in the original, right? So therefore, the distance metric from top to bottom is the reciprocal of the p-adic distance metric.
Fine. Did we figure out? I have to ask one question here. Did we figure out for one of these systems, this was our optimized way of doing it, right? My question is,
that's the transitive reduction in the rule case.
Right. I was going to ask one thing. What is the branchial structure of this thing? So if I take this and I say, evolution causal graph, and I say, why is this taking forever? You know what, I think I'm running in some crazy prototype version. Let me open this in a real version. This was a mistake. Hold on 1 second here. Let me just delete this because otherwise I'm going to get messed up again. Okay, so here, branchial structure. Okay, let me just check I'm running in the version I think I'm running in. Yes, good, good, good. It's a properly cooked version.
You probably want to get rid of the layered digraph embedding. Doesn't make a whole, and the aspect ratio, which don't make a whole lot of sense for a branchial graph. And also, I think 10 steps maybe. I don't think there's any branching left at 10 steps. I don't think there's any branching left at 3 steps.
Boring. Okay, so let's try power. Let's try 2 to the 10 times 3 to the 7 or something here. Okay. Okay, so now let's go t steps, and let's make a table here. T goes to, what do I do? 10.
I mean, we already showed that these are all going to be grids, right? If you have 3 distinct, we demonstrated if you have 3 distinct prime factors, if you have n distinct prime factors, it's going to be an n-dimensional grid.
Okay, so you're saying times 5 to the
yeah. If you make it 5 to the then it'll be a 3-dimensional grid, which will decompose into 2-dimensional slices. If you add 7 to the whatever, there'll be 3.
I put a tree-like graph in the chat that is using the Pythagorean numbers.
I don't quite understand this, but let's see it.
There is an arrow from the odd leg to the hypotenuse in a primitive Pythagorean triangle.
Okay.
And it's tree-like.
It better be, right? Because every Pythagorean triple, this is an awful lot of, let's run it for fewer steps. Let's just run it for 5 steps just to understand what this is like.
That's the initial condition, not the step count.
What did I have before there? 19?
19.
Okay. Okay, so if I now say, I should see some Pythagorean triples if I start saying vertex labels, right?
You could just do states graph.
Oh yeah, silly me.
Also, it's kind of interesting. This is a bit like combinators. You remember in the multi-way evolution graphs for combinators, they start off as a path for a while.
Yeah,
and then suddenly
know.
rapidly.
What the heck are these numbers?
Any arrow is a primitive Pythagorean triangle.
Also, if I start with a 3 here, 3, 5,
Yes.
5, 12, 13, 13. Okay, so those are pieces of Pythagorean triples.
Yes, from leg to hypotenuse. The other leg we can obtain it using the formula.
And do they branch more than, do they have more than double branching? No, because those are...
Yes, it's a power of 2. The branching is a power of 2, and we will have arbitrary large branching.
Okay, there we go. So there's a, so starting with 3. Okay.
The branching is the number of different prime powers in the factorization of the number.
So by the way, you could draw this, a nice way to embed this in three-dimensional space, since these are Pythagorean elements of Pythagorean triples, you could draw this on the surface of a sphere, could you not?
Yes, and there is a construction, the name of the construction is Theodorus spiral. That is putting one triangle adjacent to another triangle, and we obtain a spiral.
Okay, so then, right, so you can embed this thing in a spiral, presumably in the same way.
Yes, the only problem is that there is no proof that it is tree-like. We see that it is tree-like, there is no proof. We don't know.
As opposed to merging.
Sometimes there is merging. For example, in 19.1, I think that there is a merging, but we don't have control when there will be a merging, when there will be no merging. Maybe it is a not computable problem. Maybe we don't know. We have no clue.
Well, I mean, you're basically solving Diophantine equations. A merge is the solution to a Diophantine condition.
Yes, but it's quadratic.
But I thought Gauss had solved those.
Yes, but in this case, because there is an interaction, we don't know whether or not there will be a ramification, there will be a conversion or not. If someone finds the answer, we will be happy, but we don't know the answer.
I would suspect that the theory of quadratic Diophantine equations is well enough understood that that can be answered. But I might be wrong.
But the problem is that there are interactions. And when there are interactions, this becomes a problem of dynamical system. For example, for 19.1, there is a conversion. I found that using empirical data, but there is I have no theoretical way to predict that.
Yeah. So you're saying for 19, if I go long enough, then if I say states graph structure here, and I go, let's say 5 steps. Okay, 6 steps.
It's 19.1.
Oh, 91.
91, yes, 91. Maybe it is too long. Let's put the small one with 2 steps. Yes. Here
how weird.
And we don't know when will happen. We have no idea when this will happen.
I think this is determinable from the theory of quadratic forms. That would be my belief. But in this case, I mean, I might be wrong. And I think you should be able to see that. I mean, I think if you think about it in terms of algebraic geometry, I think you would have a chance of seeing that. And I would think about, well, I'm not sure whether the symbolic version of this, where you're just taking arbitrary numbers here, what that looks like. I'm not sure. Anyway, let's return to let's return to what we were talking about before. which was the
there's a well-developed theory of equivalence between binary quadratic forms in terms of linear transformations with certain, I think, with modular determinants that might be usable here. Because I think that's a purely geometrical theory that describes the necessary and sufficient conditions for equivalence of binary quadratic forms.
These are not are they binary quadratic forms? Is that all that matters here? By the time you've got many iterations, it's not obvious to me. By the time you've got a bunch of iterations, it might not be binary quadratic forms anymore.
I agree. When taken from the initial condition, they won't be binary anymore. But at the level of it, if you think of an individual branch pair,
yeah,
and you're asking,
right.
is that going to convert? That's a binary quadratic form, and then
yes,
we know. Yeah, sorry.
So let me point out, this is a branch pair that converges not after one step.
No, sure. But it's still, the point is it doesn't have to, the binary quadratic forms don't have to be equivalent after a single step. They just have to be equivalent. And the point is, as long as they emanated from a single point, they will still be binary. I think.
That sounds like a relevant theory. I agree.
And yes, so then there's a major theorem that says as long as you have a linear transformation, if there's a linear transformation with some condition on the coefficients that has a determinant of either 1 or -1, then you can consider the binary quadratic forms to be equivalent. And I need to go look up the literature on that, but I think that might be relevant.
So
or if I were going to try and prove this, that's what I would do.
Okay, let's return. And Jose had also pasted an interesting claim about spinors, which I would really like to go back to. But we were still looking at our Helmholtz decomposition, and okay, what is the definition of spinors? Who would like to attempt? We've got the notion of essentially vectors here. And we've got the notion of essentially P tensors, P forms, and so on here. What's the definition of a spinor in this setup? That would be a highly useful thing for us to know, because it obviously relates to the whole fermion story.
We need something like Penrose stairs, but exactly what, I need more time to think about it.
Why on earth is the Penrose, this was the thing that the young Roger Penrose drew, these things, right?
Yes.
Why is this related to spinors?
Because it has a non-trivial first cohomology class.
Yes.
Explain.
That's, the Penrose stair, or the Penrose triangle, that's the minimal case of a first cohomology class that's non-trivial.
How on earth is this related? This is a picture that is cheating in terms of perspective. Why is it related to cohomology classes?
Because it's cheating. It is cheating because of the problem with the cohomology. If the cohomology was fine, it will be no cheating. And the spinors are cheating in our universe in some way.
Okay, so explain this. Could you explain, Jonathan or Jose, or either Jose?
Yes, the idea is to first to define a Penrose stairs in the Wolfram model, and after that to go to the spinors. Because
I understand that flow, but I don't understand. Explain the relationship between cohomology. So, okay, Jonathan, could you, given that you understand, or maybe the other Jose, explain in first principles how cohomology might work in our setup.
Oh, you're not still asking about the tribar?
I am asking about the tribar. Yes, you can explain the tribar. Yes. Okay, go ahead.
Well, that's just saying that the fact that there's that the first cohomology group is non-trivial is just saying that there's an if you try and project the whole tribar onto an annulus, there's an obstruction, right? So even though locally everything's okay, globally there's an obstruction, right?
Yes.
And that's basically, I mean, that's the sort of intuitive definition of the first cohomology group.
Okay, well, so let's understand that for our models. This should be really understandable. This should be not that hard. Okay.
I'm pretty sure we discussed this in the category theory discussion. We talked about generalizations of cohomology classes.
We did, but let's try and bring them down to earth, so to speak, and see whether we can, because if we can get an analog, you know, just like we're talking about p-forms, right? What we want to do for spinors is talk about something where essentially p isn't in, you know, is a half integer. That's in some very rough terms. That's what we're talking about there. Maybe the other Jose has a comments about this.
I think that there is a symmetry. S2 symmetry.
Yes. We have to break the
Jose Manuel, in my case.
Go ahead.
Okay, so some comments about the spinors. So this is difficult. So my first comment is that spinors are truly geometric objects, as geometric as vectors. It's just that our brain is not well equipped to think about them. So the only way we have to think about them is by creating non-punctual things, like bigger objects. And there are examples with belts, and these examples with the Penrose stairs, and very are topologically non-trivial. But the truth is that it should be as easy as a vector, just that we cannot understand it.
Okay, so then our challenge is to, I mean, great. Okay, then our challenge is.
Let me say one more thing. So the standard typical phrase that it's used to describe spinors is that they are square roots of vectors.
Mm-hmm.
And this comes from Clifford algebra, in which we have the same thing of the Dirac matrices, in which you were able to solve something, and then he realized that with something whose squared was the identity, it was solvable, right? You know all the story. So there is this square root process there, which I think it's illuminating, but it's very algebraic. It doesn't give you a geometric picture, and that's what we would like to have, a geometric picture.
All right, I'm going to make a guess, okay? Crazy guess. Imagine, what is the difference between a digraph and an undirected graph? Okay, crazy guess might be that thinking about vectors in hypergraphs might be something where we are allowed to go two ways on our hyperedges, and thinking about spinors might be allowed to go only one way on the hyperedges. Is that insane? And by the way, that would not be completely unrelated to the whole branch pair convergence story of, you know, for fermions, if that was the right picture. So, question.
I could say that we need to go twice in order to return to the same place.
Right.
So every time that we make a cycle, we change our state, but we make another cycle and we return to our initial state.
Yeah, but okay, but so this question about your tribar picture, right? Mm-hmm. It could be the case that in one of these graphs, you can't make that if every edge is undirected, and you can if it's directed.
We can imagine an auxiliary graph that is a copy of the original graph, and we go from the original to the auxiliary, and we return to the original.
Yeah, I understand, but I think what you're thinking about there is, let me think about this for a second. Okay, question, can we construct, okay, what is the graph theoretic analog of one of these tribars? What is cohomology? Okay, most basic questions. What is cohomology in graphs?
There is a lecture about it. I remember in YouTube, there is a lecture about it, but I don't remember exactly. Looking for cohomology
Jonathan,
graph, we find it.
Do you know how cohomology works for graphs?
Well, yeah, I mean, it works basically the same way it works for manifolds. You have some algebraic structure, it tells you something about the combinatorial and topological structure of the graph, right?
So the graph theoretic analog is a graph with no trivial cohomology.
Okay, but help me out more concretely. So I'm just looking at random papers here about graph cohomology, but can we be concrete? Okay, so if we say, what do I do? What? Okay, how do I define? I've got some random graph here. Okay, here's my graph, wherever it was. One of these things. There's a graph, right? What do I do to define cohomology on this graph?
Well, I mean, that's what we were doing before, or that's what I was trying to say we should do before, right? I mean, we have the simplest cohomology. Okay, so you have a given graph. You want to construct a simple chain complex. Kind of the simplest one you can do on any principal ideal domain is one where the only non-trivial homomorphism is the boundary operator, which is the thing we defined before.
Okay.
So then the homology of that chain complex is the ordinary homology of that graph.
Okay. So look, what we're trying to understand is, so a result about spinors, a result about, for example, the whole set of results about, 2 pi versus 4 pi and, rotation of vectors, rotation of spinors, things like that. Is there a direct way to understand that in terms of graphs? So rotation in a graph, we don't know how many dimensions we're in, so I don't understand the 4 pi, 2 pi stuff, but I don't understand this double covering business because I don't know how that works for arbitrary d-dimensional space. Maybe somebody else does. But the notion of rotation that we're imagining is you're anchored at a particular point here, you look at the surface of this geodesic ball, and your rotation is where you can move on the surface of that geodesic ball. Correct? So if we thought about it that way, there is something kind of interesting that happens if we're in a directed graph versus an undirected graph, I think. Is that making sense to anybody? Look, let me do something very concrete here. Let's make.
I mean, I think we understand what you're saying, right? That any undirected edge can be treated as a pair of directed edges, and so naturally the rotation group that covers one will produce a double cover of the other.
Yes. Right.
Yeah, I agree. That's
seems not completely uninteresting for this purpose, right?
No, but I thought okay.
What have I missed?
Nothing. No, it's just that I don't know, a few weeks ago when I gave that sort of colloquium about spin statistics, I thought I covered all of this.
About spin statistics? Wait a minute. I thought you were talking about.
In the lead up to the geometric formalism one, I presented some results about generalized automorphism groups and double covers in rotation groups.
Yeah, I only understand when I've understood it myself, and I think I didn't understand it myself, but maybe you already figured all of this out. Okay, so the basic claim is, the rough thing is directed edge needs to be doubled to make an undirected edge. But I mean, more concretely, I don't quite understand how that, so if I make this from directed edges and then I say, so this is the directed version, and then I say highlight graph GGG, and then I say neighborhood graph, let's say vertex 20, GGG, vertex 20, 4 steps, 5 steps, whatever. Okay, let's do graph 3D. Okay, great. So that's our undirected version. No, that's our directed version. Now let's do our undirected version. Okay, now I'm a little bit confused, but that's hold on. What am I supposed to see here? These will be different, right? They better be different. Well, here, let's understand this. How do we make a directed? Oh boy, I just want to make a random directed graph. How do I make a directed graph that's like a triangulation of something like that? A planar, can I make a random planar graph? Do we have a way to do that? Voronoi triangulation of something that is directed. Or Jonathan, can you help with this? This shouldn't be the same, right? This should have picked out different vertices for the neighborhood graph. Oh, shoot. Neighborhood graph doesn't deal with directedness. That's the problem here. But in general, we will have a smaller geodesic ball in the directed case, right?
Mm-hmm.
Really what I want to do here is to say, let's see, what would I do? I would say subgraph here. I don't quite know how to do this, but if I'd say subgraph of GGG, select vertex list. Am I doing the wrong thing here? Vertex list of GGG, comma, graph distance from, in GGG, from hash to vertex 20 is less than 5, right? Am I right?
Sorry, I was writing the code you just asked for. I think that should do it.
Okay, let's see what you wrote. Let's actually just do this the other way around. Okay, so that's in the directed graph and that's in the undirected graph. They're very different. Okay, what's this now? So this is making...
It's making a random Delaunay mesh and then the associated triangulation.
Okay, cool. Let's make 50 points here. Actually, probably what I want to do is make that a bit bigger, don't I? I don't quite understand why that's doing, but anyway, never mind. Let's say 70 points or something here. Okay, so now let's define this to be GGG is that. And now let's go ahead and, okay, so this will be the undirected. Oh, for okay, that's the undirected version starting from, let's start from node 1 maybe. Great. Let's start from graph center of GGG. Wow, that's really weird. Why does it go in 2 steps? It goes that far? Oh, that's the undirected version, right? That's the effective undirected version.
Right.
And now if we do the directed version, let's see, from graph center, less than 1, less than or equal to 1. What? Okay, let's see, what is graph center of GGG? Oh.
It's an equivalence class.
Well, therein lies our problem. Okay, let's replace that by like 13 or something, ag. That's hardly the center of that graph. Shocking. Okay. All right, a bit boring, but this is an attempt to show the difference between the directed sphere and the undirected sphere. So in what sense is the double cover of the directed sphere the undirected sphere? From here. So I do think, I mean, so maybe this was obvious to you, Jonathan, and maybe I realized this months ago as well. But what does, I mean, this idea that directed edges are associated with spinors and that undirected edges are associated with vectors does seem like an interesting idea.
Right. I mean, it's not quite that straightforward in the hypergraph case. I think it's more naturally stated in the multi-way evolution graph case. The point is that when you have a branch pair that resolves, what you're saying is that you can describe both branches by essentially a single edge, a single vector, right?
Yes.
But when you have a branch pair that doesn't, you have to use two.
To what?
That you can't form an equivalence relation that treats both branches as the same. You have to treat them as separate objects.
Yeah, but so what? So what is it? So where does that? I mean, I understand that's presumably related both to spinors and to fermions. But walk me through that.
The thing I was presenting a few weeks ago was this explicit computation where I was looking at the generalized automorphism groups that are these rotation transformations, and then saying, okay, so then effectively what that means is if you take the one-step branch pair convergent multi-way evolution graph, and you look at the rotation group on that, and you ask what rotation transformation is necessary to translate or to transform a geodesic from one side of the space to the other, then you look at the associated multi-way evolution graph in which everything diverges. Well, then you have a factor of 2 more points to rotate through. And so the rotation transformation that would have got you from one side to the space to the other only gets you halfway.
I do remember this now. I don't remember the details of it. So walk me through that again. So you're saying if I had a grid.
If you let me share for 1 second, I can share the notebook quickly.
Is it in the archive, Jonathan? Did you put that?
No, but I can add it to the archive because I think it might come in useful.
I think so.
Okay, so here's the basic idea. So we have a grid graph like this. You have a geodesic, which is some generalization of a vector. And then you can look at the automorphism group for this graph, and you can ask for the subgroup of the automorphism group that corresponds to the transformations that strictly preserve the length and the origin point of that geodesic. So this is one example.
Yep.
So the origin point is the same, the length of the geodesic is the same, but it's now ending up in a different place. And so that's our analog of a rotation transformation on the space. And so the argument is that that subgroup limits to something that we can think of as being a bit like the rotation group. Although, I mean, there are some additional conditions, because the transformations that preserve the length and origin points of GD6 are strictly more general than the rotation transformations. You have to impose some divergence conditions, but basically that's the idea. Okay, so then if you have a multi-way system in which every branch pair is one step convergent, you can take, you can take a geodesic like that. You can look at rotation. You can again look at the subgroup of the automorphism group that preserves the length and origin point of that geodesic. You get things like this. That's a generalized rotation of that geodesic there. Then if you do the same thing for one of these multi-way systems in which nothing converges.
Okay, hold on. So rotating in branch time is not something that I'm completely familiar with, because that's what you're doing here. This isn't a rotation in space, it's a rotation in branch time.
Right. Right.
Which, but for some bizarre Wick rotation, is not a rotation in space-time.
Mm-hmm.
Okay. But I don't think actually it's that much harder for hypergraphs than it is for ordinary graphs. But anyway, okay, so you've got, the basic point is you're making a statement about rotations in graphs of, the directed edges in a grid-like thing where you're converging in one step. And you have a certain automorphism group associated with that, with the set of things that, let's see. Yeah, with the equivalence class of things that end up at the same point. Okay, now consider the case where they do not converge.
Right, right. And so then, as I say, the basic intuition is, whereas before, if you had to rotate through n points to get from one side to the other, now you have to rotate through 2n.
Why?
Right. Because if you think of how many states there are going to be so for the kind of bosonic convergent case, in the limit, the ratio of the number of nodes on one hypersurface to the number of nodes on the previous hypersurface tends towards 1.
Yep.
But in the fermionic or the non-convergent case, the limit tends towards 2. So in between time t and time t plus 1, if you apply a rotation transformation in the bosonic case, that same that rotation transformation has to rotate through on the order of n points. But for the fermionic, the non-convergent case, it has to rotate through on the order of 2n points. Right?
Hold on. You're saying,
which I can show explicitly. I mean, if you just take the hang on. Yeah, so hang on. This is a rotation transformation as applied to one of these strictly non-convergent multi-way evolution graphs. So then if you take okay, so let's consider the rotation transformation that would transform you from this side of, branchial space to this side of branchial space. That's like, that's a pi radian rotation or something. Then you look at you apply the same automorphism group, but for this non-convergent case, and you end up rotating from there to there, which is only halfway across. And then you'd have to apply it again to rotate to the other side.
Wait a minute, what do you mean same automorphism group?
So you have to, okay, this is where it gets a little bit complicated. You have to canonicalize you have to effectively take an index graph. So you have to canonicalize these multi-way graphs. But you can ask, if we have two graphs of the same size that have the same vertex indices, but one of which has every branch pair converging and one of which has every branch pair diverging, you can apply the same automorphism group. You can apply the same transformations to both and see what they do. Right.
Yeah, I understand that.
So then the point is that you can ask, what if you take a transformation that would have rotated you from one side of branchial space to the other in this case, what's it going to do in this case? And the answer turns out to be it translates you only halfway across, or transforms you only halfway across.
Okay, so look, this coordinatization of branchial space that we keep on grappling with, that relates to this whole phase in the interference, quantum interference and so on, and this fermion stuff, these seem to be closely related.
Yeah, totally.
Okay, so wait a minute. So what you're basically saying is, and that's also going to presumably, boy.
Right. So I mean, here's where it kind of makes connection to what we were talking about, right? That if you look at one of these immediately convergent diamonds, you can think of this, you can think of a vector going from this point to this point, and in a sense, you don't care about the fact that there are these two different paths for getting there because they're kind of treated as the same. Whereas in the non-convergent case, you can't do that. So this is like your your undirected edge versus your directed edge over here.
Why? Why is it like the undirected edge?
It's like the because in the undirected edge, in the undirected edge, you have two. Effectively, it's like you have two directed edges.
Yeah, I can see you have two directed edges, but normally they go the opposite directions.
Right.
They're going in the same direction.
That's the part where I'm saying I think I disagree a little bit with the characterization of hypergraphs and why I think it's easier to think about in the directed multi-way graph case. Because the point is, it's not the case that vectors are invariant under Z2 transformations, which is kind of what you're implying. Right.
Well, let me put it a different way. One feature of Euclidean space is that you can go forwards and you can go backwards.
Right.
In this grid, you can go forwards and you can go backwards. Whereas in a tree, you cannot do that.
Right. But crucially in Euclidean space, because you can go forwards and because you can go backwards, it's meaningful to distinguish between forwards and backwards. In other words, your vectors are not invariant under Z2 transformations. Right.
Yeah.
So they're not, it's incorrect to think of them as being undirected GD6. Which is why I think it's easier to describe in this case.
Well, but the main point is you're saying we form Euclidean space we form integer dimensional Euclidean space here. The thing that I'm not getting yet is in what sense, what is the spinor analog? Okay, here's a very basic question for you guys.
I can stop sharing.
Well, I don't know whether you should stop sharing because I think that was the most relevant thing. But anyway.
Okay. I'll stop sharing again.
What's that?
I'll start sharing again.
Yeah. Okay. So what you're arguing is this limits to ordinary Euclidean space, where you can define vectors.
Well, no, I mean, my basic point is, in the scheme as you described it, it sounds as though V and minus V are the same. If I invert an undirected geodesic, I get the same undirected geodesic. So in other words, vectors are invariant under Z2 transformations, which is not true in Euclidean space. So what I think you have to have is the same basic idea where, in effect, your single edge is actually represented by a pair of edges. But instead of them being a pair of edges in opposite directions, so you get the Z2 invariance, instead, they're a pair of edges going in the same direction, which is what you get when you have a branch pair convergence. So that's all I'm not saying anything deeper than that.
Okay, come on, we're very close here. Let's just push this one more. Let's see if we can push this rock over the top of the hill before I have to go to my next completely different discussion. Okay, we are trying to understand what is a spinor and how does it relate to, fermions. And you're saying that it is natural to define vectors. The claim would be, it is natural to define vectors in a grid graph. It is natural to define spinors in a tree. It's basically what you're saying somehow.
Right.
Okay, let's walk through that one more time. Okay. How do you define, so a vector here, this is a directed graph, but a vector is being defined in the branchial direction. Right? You're not defining a vector going down this picture, are you? You're defining a vector in the spatial slices of this thing. Is that true?
Well, they can actually be either.
Now you're confusing me. I mean, you think then it's a space-time vector in this picture.
Yes. You can have. You can have either. It's not a space-time vector; it's a branch-time vector, but the idea is the same.
Yeah, it's a pity we can't do this for a causal graph as opposed to a multi-way graph. But anyway, because then we'd be more directly in space-time.
Right.
But perhaps we can do it in space-time. I don't know. But anyway, let's look at it here in branch time. Okay. So then you say there's a vector in branch time that is defined by, what's the point here? The point is you've got an equivalence class of vectors that are the vectors of a certain length, right? Mm-hmm. That equivalence class of vectors can be thought of as the vectors that are on the surface of a sphere.
If they're emanating from a single point.
Right. It's an equivalence class of vectors of the same length. Okay. Now, in the tree case, you also can have an equivalence class of vectors of the same length, but the number of such vectors is much smaller than it is in this grid case, right? In the grid case, there are many, many different vectors which wind up being the same length. Walk me through that. Okay, so in this case, any vector that winds different, in the tree case, you have to commit yourself to which edge of the, which sequence of edges on the tree you're going down.
Okay, here's a straightforward way of viewing it, right? So I'm at a branch-like hypersurface that corresponds to some particular time t.
Yep.
In between time t and t+1, I want to apply a rotation transformation. I want to apply a rotation transformation that's going to transform me from pointing in one direction in branchial space to pointing in the opposite direction in branchial space. Right? That's like this translation here, this transformation, right?
Yes.
Make sense?
Yep.
Right. Okay. So in the convergent case, the number of states that I'm going to have to move between on the branch-like hypersurface is of order n.
Yes.
In the non-convergent case, it's of order 2n. Or to put it another way, the rotation, if you look at the group for the rotation transformations for the non-convergent case,
why is it of order 2n? Hold on. The number of things you have to move through, I don't understand what you mean by move through. I mean, in other words,
if I have n states on my current branch-like hypersurface,
yes.
In the convergent case, I will have n+1 on the next step. So the ratio between the two as it converges to 1. So anyway, what we have is something of order n. In the non-convergent case, I will have 2n.
No, wait. I don't understand. You're trying to move that vector to the other side, right?
Yep.
What do you mean by move that vector? What are you going to do? You're trying to take the pieces of that linkage and move them one step at a time to the other side, or what?
I'm just going to do what I'm doing here, right? I'm going to apply an automorphism group transformation that takes this, that takes all the points along this vector and maps them to all the points along this vector.
Mm-hmm.
So the point is, on my current branch-like hypersurface, how many points are being swept through in that transformation? The answer is of order n. Right?
What's n? N is the
number of states on the current branch-like hypersurface at time t. n+1 is the number of states on the branch-like hypersurface at time t+1.
Yeah. Okay.
Right. For the associated divergent case, the number of states I'm going to have to sweep through for the same transformation is of order 2n. Because between any pair of neighboring branch-like hypersurfaces, there's a doubling in the number of states. That's what it means to be divergent.
I don't understand this. I'm sorry. Let's go back again. Okay, so you're saying, what do you mean by sweep through?
So suppose I didn't want to apply the transformation in one go. I wanted to just, I wanted to apply it kind of piecemeal, so that you were never translating by an ancestry distance of more than 1 at a time. In other words, so it was a local transformation in the branchial graph.
Yep.
Then the number of transformations I would have to do in the convergent case is of order n, because to get from this point to this point, I have to do of order n. I have, the ancestry distance is of order n.
Whoa, wait. Multiple things are going on here. Are you talking about getting from that endpoint to the other endpoint?
Yes,
because,
right.
Okay, so in that you can just zigzag going back one step, right? You just zigzag back on the previous step. You don't have to go all the way back to the root to get there.
Right, but the point is I have to do n of order n local transformations to do that.
Or n transformations, each of which goes back only one step.
Yes, each of which is local in branch.
Well, it goes back one step. Whereas in the other case, what you're saying is you have to do but I mean, this is you have to go all the way back to the root to be able to get to the other side, right? To get to the other side, to get that last point. Okay, the number of moves you have to make here. Look, you can go from the right-hand end to get to the left-hand end. You're going backwards down up that branch pair there. No, not all the way. Just one step up the branch pair to there. Now you're going back down.
Right. Yeah, but the reason why that's the case is because the branchial graph distance and hence the common ancestor distance between the two is of order n. But yeah,
yes, I understand. The ordinary branchial graph, I mean, if we had these thickened branchial graphs, we would have a better story. I mean, really, it's the ancestry distance between, well, no, it's not right. It's look, to get from one side to the other side, if you insist that every move be ancestry distance 1, then there are n such moves that you make.
Yes.
In this case, right?
That's all I'm saying.
If you insist that the things are ancestry distance 1 in the tree case, there are 2n such moves that you make, right?
Right. Yeah, I mean, I'm not saying anything sophisticated. That is literally all that I'm saying.
Right. So
therefore, if you take the group of such rotation transformations for the tree case, they will naturally form a double cover of the rotation transformations for the non-tree case.
Okay, let's just remember what transformation we're making. We are making a 1 ancestry distance transformation, right? Nick is suggesting making a movie of this. Yes, we certainly could, right? So it zigs at the bottom there. It zigs along down the bottom of that picture, right? Whereas in the other case, it has to go all the way up to the top of the tree. So let's look at a tree again. Could we just look at a tree again and understand what it actually does to get there, right? So what it has to do is it makes an ancestry distance 1 move. I don't understand. I don't understand again, because it's not the ancestry distance 1 move. You can't get there from here. It's got to go ancestry distance 2 to get across. It's got to go ancestry distance. I don't understand. I don't understand these moves that you're making here, right? Because you've got to go. Ancestry distance 1 moves cannot get you from one side of a tree to the other.
Right, which is why I'm saying that they have to be local, right? So in other words, locality meaning, in the standard definition of locality, in m steps, you can only go a distance of order m.
I don't get this. I'm sorry. We have to do it more explicitly. I don't get it. I mean,
what could be more explicit than actually having the rotation group, the automorphism group transformation applied to this graph? What more do you?
Well, okay. So what you're doing in those automorphism groups is you are saying they are permutations that leave the graph invariant, right?
Right.
They're permutations of labels that leave the graph invariant. And you have that both for the grid case and this tree case.
Right.
And you're asking how many elements of that automorphism group do you have to apply to get from one point to another? Is that correct?
Right. Well, I mean, okay, so obviously the big picture idea is if you look at the subgroups of the automorphism groups that preserve the lengths and origin points of GD6 for the case of a grid graph, you will get something like an orthogonal group. And then the conjecture is that in the associated tree graph, you get something like a spin group. In other words, you get a double cover. That's the.
No, I understand the conjecture. Okay, we are really close with fermions, spinors, spin statistics. We're really close. And to relate this, we then have to connect our angular momentum argument to this to understand the spin. Right? Relate this to this question about, computing angular momentum in a particular direction. I unfortunately have to go to something completely different. I apologize. We've completely failed to discuss experimental aspects of this. Well, we had an interesting conversation. Jose Manuel is asking about supersymmetry. And I think you had an argument about that previously, right?
Right. I mean, obviously, it relies upon us all agreeing upon this particular formulation, but
which we don't yet. But
which
yeah,
we don't. So it's kind of a moot point. But my argument was simply that, and it's, by the way, it's related to okay. So there is this purely algebraic idea, right? That if you think about representation theory and you look at the representations of the Lie algebra for the orthogonal group, then there are the representations that you can construct by tensor constructions, and then there's all of the other ones, right? And so the tensor construction ones are kind of the special orthogonal ones, and then the other ones are the spin representations. Yep. And so translated into this context, my claim was that what you're basically saying is if you have an arbitrary multi-way evolution graph, you can decompose that into the set of branch pairs that converge and the set of branch pairs that don't converge. So in other words, the things that are described by the special orthogonal, whose transformations are described by the special orthogonal group, and the things that are whose transformations are described by the spin group. And so then if you think about that in the, or to put it another way, you can kind of factorize the overall multi-way system into the convergent branch pairs and the non-convergent branch pairs. And so then the analogous claim in supersymmetry is that therefore the associated Hilbert space that you're generating is decomposable into a direct sum of the fermionic piece and the bosonic piece. And therefore you have all the kind of the standard supersymmetry generators you would expect. So it ultimately comes down to the fact that the Z2 grading of the Hilbert space results from the fact that all branch pairs either converge or they don't. That was my claim, but it requires us.
Right, and I mean the basic claim here, the basic meta claim, which again we need to unravel. The reason there are just fermions and bosons is because things either converge or they don't. The reasons that it's essentially something related to directed versus undirected that is leading us to spin groups or spinors versus orthogonal groups. And I mean, what this is going to do, which is really interesting, is it's going to make natural a spin statistics connection, which has never been terribly natural to me before. Well, I mean, the measuring the spin is a whole different thing. I have to go to a different meeting. I'm sorry, guys. Look, I appreciate the, and Jonathan, I would like to ask you some other things if you're around a little bit, but I got to go to something else right now. All right, thanks, guys. See you all soon. Got to run.